Hello friends, welcome back to my YouTube channel. This is Ramdas Pandit Bharsat, working as Assistant Professor in Chemistry at Maratha Vidya Prasarak Samaj, Nasik. In this video lecture, we are going to study about important conclusions can be drawn about the equilibrium constant. Now, some conclusions are given for the equilibrium constant. If you will see the equilibrium constant for the reverse reaction, okay, so the reciprocal of that for the reaction return in forward direction, okay, so that will be the first important of the conclusion, okay. And when the balance equation for the reaction is multiplied by factor n, okay, the equilibrium constant for the new reaction is the original constant, okay, it will be the original constant and raised to the nth power. So you can write in this way k new, okay, k is for the new is equals to the in bracket k original, okay, at the power nth. So this conclusion you can write for the equilibrium constant. Now for the second conclusion, that is the magnitude of kc or kp is a measure of the extent to which the reaction occurs for any balanced chemical equation, okay. If you will take any kind of balanced chemical equation, so there will be the magnitude kc and kp, okay, it will be the extent the measure, right, and that will be the it constant at given temperature and it change as temperature changes, or you can say it does not depends upon the initial concentration, okay. So this will be depends on all these three terms, right. Now we have to see next topic, that is equilibrium constant and extent of reaction, okay. So the Gibbs free energy of reaction mixture, that is denoted by delta G, that is totally depends upon the partial pressure and concentration of reactant and product, okay. So Gibbs free energy depends on the partial pressure and concentration, yet you have to know. So therefore the tendency of the reaction to go in the forward or the reverse reaction is determined by this pressure or concentration, okay. So whatever the tendency of the reaction, it will be depends on the pressure and the concentration of this solution, right. Now the delta G is changed during the reaction as the proportion of reactant and product change, okay. If you will change the proportion of reactant and product, so you will see the change in Gibbs free energy. And one more thing, the composition of the reaction mixture at equilibrium is the composition at which delta G is equals to 0, right. Equilibrium condition, that will be the there is no any kind of change in Gibbs free energy, okay, that will be the 0. Gibbs free energy will be 0. Now you will see the first case, okay, that is if you will take some reactant, okay, pure reactant, pure product, and you will see the graph here. On y-axis Gibbs free energies, okay, there, and on x-axis you will see the progress of this reaction, okay. Now here you will see the graph from this way, so it will be go like this here, okay. This is the equilibrium condition. So at the initial stage you will see here, okay. So what will happen if the k is quite small, okay, k is less than 1. So the equilibrium is established when the most of the reactant remain unreacted. Such a reaction is reactant favor, okay. So you will see here most of the reactants are remain unreacted here, okay. So there will be the this kind of reaction will be reactant favor, okay. It means there is no more reacted, okay, like the product. You will see the reactants are unreacted remains as it is, so we call them that is condition for the reactant favor. Okay, and you will see the equilibrium condition is got here. Okay, within a unreacted reactant, right? This is for the first case, and you will see here at the equilibrium stage there will be the Gibbs free energy will be 0, right? So uh, it is the reactant favor condition, right? Now the first condition is there. Now you will see the second condition. You will see on y-axis again gives free energy, on x-axis again you will see progress of reaction, and this will be graph like this. Okay, so here will be the equilibrium condition. Okay, so you will see the product of concentration is much greater, right? Okay, product of concentration that is very high than the reactant. Okay, reactant concentration. So the at equilibrium most of the reactants have been converted into product. Okay, so you will see here most of the reactants species are converted into the product, so it will be the product favor reaction. Okay, after the equilibrium condition you will see, okay, here most of the reactants are converted into the product, right? So this is for the second condition. Equilibrium condition we have to remember here. Okay, so the delta G is equals to 0, that is the equilibrium condition is here. Okay, and here will be the Gibbs free energy is less than 0, and here again right here will be the more. Okay, Gibbs free energy will be more than 0. So this is for the second condition. Now for the third condition you will see Gibbs free energy on y-axis, okay, on x-axis progress of reaction. So here will be the k is equals to 1. So the equilibrium will be, you will get exact at the center. Okay, so here will be the Gibbs free energy will be 0, pure reactant and pure product. See here, so the both reactant and products are present in the substantial amount at a equilibrium. Okay, so both whatever the species, whatever the amount of a reactant and product will be same at a equilibrium condition. Okay, at a equilibrium stage. So this is for the third type of condition. Now we have to see the distinguish between delta G and delta G 0, right? Now you will see here Gibbs free energy of the reaction mixture delta G, that is totally depends on the concentration of the reactant and product during the course of the reaction. Okay, we have to remember this thing. Okay, whatever the concentration of the reactant and the product during the course of reaction, okay, concentration of the both reactant and product, okay, it is affected on the Gibbs free energy, right? And the equation will be delta G is equals to delta G 0 plus RT ln Q. Okay, equation react. Now see, Q stands for the question reactions. Okay, reaction question, which is the ration of convention of the product raised to proper power to the concentration of product of reactant raised to proper power. So you will write here at equilibrium delta G is equals to 0, Q is equals to K, and delta G 0 is equals to minus RT ln K. Okay, now delta G 0 remains constant during the reaction and it does not change with the composition of the reaction mixture. Okay, so delta G 0 is the difference in molar free energies of the product and reactant, right? And delta G is the difference in molar free energies of the product and reactant at a specific stages of the reaction. Okay, so we have to remember this thing, difference between the delta G and the delta G 0, right? You will see the difference of this. Okay, delta G is the difference in the molar free energies, the product and reactant in their standard state. Now we have to see the example based on this. You will see here a 50-liter reaction vessel contains 1 mole nitrogen, 3 moles of hydrogen and 0.5 moles of ammonia. Will more ammonia be formed, or will it dissociate when the mixture goes to equilibrium at 400 degrees Celsius? The equation will be nitrogen in gas form plus hydrogen in again gas form and ammonia. Formation of ammonia is there. Okay, so the Kc is 0.5 at 400 degree Celsius. Okay, so the solution we have to find out first of all the concentration in mole per liter. Okay, so for the every species you will see ammonia we have concentration of 0.5, right? Ammonia, all right, and divided by out of 50 ml. Okay, whole solution we have 50 ml, so 0.5 divided by 50. For the whole species we have to do same thing, 3 for the hydrogen, right, and nitrogen for the 1. Okay, so that you will get for ammonia 0.01 per mole, and here hydrogen 0.06 per mole, and here nitrogen you will get 0.02 per mole. So the dimensional concentration will be ammonia is equals to 0.01 and hydrogen 0.06 and 0.02 without unit. You will get these terms. So the Q is equals to ammonia concentration of ammonia square divided by concentration of nitrogen into the concentration of hydrogen cube. So the you will write in this way ammonia. Okay, you have to take simple square. Okay, and a nitrogen 0.02 into 0.06 cube. So the after calculation you will get this thing, that will be the Q is greater than K. So the Q will be here is equals to 23.15, right? And that is the Q is greater than K. So the reaction will be go to the left as it approaches equilibrium, and ammonia will be dissociate here. Okay, at this stage.